Hi guys, welcome to the second video of this reaction kinetics. Now in this video, we're going to learn the second way to determine the rate law and the order reactions of a chemical reactions. Alright, now look at that. This is the table given as experiment 1, 2, 3. So which means the same experiments that involve a reactance of A and B. God knows what's the product, doesn't matter because we are focusing on the reactants. So in this case, we can see we have reactants A and reactants B in terms of concentrations, and we repeat the experiment using different concentrations of A or B. All right, and there are 3 experiments here. You see that? So let's check it out. What's going on here? For the first experiment, we are using 0.1 mole per dm cube and 0.1 mole per dm cube of both A and B, and the initial rate was measured at 4 times 10 to the power negative 5. All right. Second experiment, we notice that concentration of A remain unchanged, but then we double the concentration of B, and the initial rate of reactions remain the same. See that? And the third reactions, we actually double the concentration of A, but then maintain the concentration of B at 0.1. You see that? Even though we are repeating the experiments, we are changing the concentration of reactant each at a time. We don't change the concentration of both reactants in the same reactions. So we have to make one of them constant while changing another one, right? Because we need a constant variables. Otherwise, how can we compare between the repeated experiments? So every single repeat experiments, we have to change the concentration of a particular reactants, but then maintain the other one constant. All right, making use of this, we can actually deduce the order of reactions based on the concentrations. Look at that. Now let's say I'm looking for concentration of A, the reactants. What's the order here? What's the order of reactions for A? So since we are focusing on A, then B must be constant. So which 2 experiments that we should compare when B is constant? 1 and 3. Look at that, constant. All right, so B is constant. We can ignore B. We just look at the changes in A and what's the result in terms of the rate of reactions. Look at that. If we are comparing experiment 1 and 3, right? Concentration of A changed from 0.1 to 0.2. Double. It times 2. From here to here, multiply by 2. And what's the rate? What's the effects on the rate when I double the concentration of A? So the rate is from here to here, of course. 4 times 10 to the power negative 5. Change to 16 times 10 to the power negative 5. How many times here, guys? 4 times. Right? 4, 4, 16. So what does it tell you from here? If I double the concentration of A, the rate of reaction increased by 4 times. Okay, that would means A is second order. Make sense? Because when I times 2, here is 2 to the power of 2 for the rate of reactions, which is equals to 4. Right? So that would means A is second order. So we're done with A. Okay, so I write it out. Concentration of A, or we write it in a proper way, guys. We learn to write like that. First is we write second order with respect to A. Why? This is because concentration of A double times 2, or you say concentration of A double rate is 4 times higher. Something like that. Okay, you can write your answer like that. And let's look at B then, because we need to come up with the rate law, with the rate equations. So we need the order reactions to complete it. So if we are looking for B now, A must be constant. Obviously, we are comparing experiment 1 and 2. All right. So if you're comparing these two, A is the same, so we don't have to look at that. But from here, we can see concentration of B is multiplied by 2, and concentration, the initial rate of reaction is actually remain unchanged. So what does it tell you? B is actually zero order. So we put zero order because there's no effect on the rate of reactions even when the concentration of B doubled. Okay, second order, zero order with respect to B. Okay, because when concentration of B double, rate remain unchanged. See that? So this is how you write your answer. And guys, for these with respect to, right, to make your life simple, these with respect to, you can write it as WRT. Okay, this is how they write. This is the proper way of writing WRT. This is they allowed you to do that, WRT, but not for the rest. Don't simply just use the letters to represent a phrase, right? So these WRT, we know that for reaction kinetic is with respect to. So in your answer, you can write it as WRT. All right. So this is how you properly write your answer when you're comparing like that. Okay. So it's so simple. And what is the rate law in these reactions, in these questions? Rate equals to K. Now K is a constant where we need to calculate later. I will show you. So rate equals to K, this is always the case, and then write all the concentration of reactants involved. Supposed to be A and B now, but we found out that A is second order, B is zero order, right? So what is the final rate equations? Rate equals to K concentration of A power 2, and this is the rate law. Because B power 0 equals to 1, where we just ignore B then. So this is the proper rate law after considering the concentrations given here. The initial rate methods, we called it. All right. Now, this is just the first method. We have another method to do that if they give you a table like that. So this is more straightforward is because all the concentration givens are quite straightforward. Look at that, 0.1, 0.2, 4 to 16. You can see the relationship clearly. Okay, but what if in exam or in the questions they give you a value where you can't see exactly 2 times? Like for example, 0.1 change to 0.15. It's not exactly 2 times. And 4 change to, let's say, 4 times 10 to the power negative 5 change into 5 times 10 to the power negative 5. So that's not a exactly double. So we can use another mathematical way to prove that, to calculate it. So I'm going to show you the second method now by using the same example. Let me erase everything here. So that will be the first method. Now is the second method where we used a mathematical way to calculate that. Okay, now how do we do that? Very simple. If we are looking for concentration of A equals to what order? Okay, we are looking for A now. Let's do this. Again, when we're looking for A, B must be constant, which is these two. So we're comparing experiment 1 and 2. 1 and 3. Make sense? So let's write out the equations for reaction experiment 1. So rate equals to K, concentration of A, which is 0.1, concentration of B, which is 0.1 as well. All right. So the rate, this is equation number 1. We're solving simultaneous equations. So the rate of reactions here, we can put in the value. Okay, we can put in the value. So the value is 4 times 10 to the power negative 5. So first equation done. Second equation is referring to third experiment, where we have 16 times 10 to the power negative 5 equals to K, 0.2, 0.1. This is equation number 2. All right, we're solving it. So let's do this. If I'm using 2 divided by 1, all right, 2 divided by 1, so K will be cancelled out, and then you have 16 over 4, right? Equals to, these two will be cancelled out as well, 0.2 over 0.1. And obviously you can see that, what is that? 4, 2. Make sense? Right? Or make it this way. Make it clear. Okay, so this is the equations. 16 over 4 times 10 to the power negative 5 equals to 0.2 over 0.1, right? So it's actually, this is power A, this is power B by right. So make it clearer. So here you're getting 4 equals to 2 power A. Since we are looking for the order, we are looking for the power, right? So it's actually this. So what's your A? So we log both sides. Log to the base 10, 4 equals to A log to the base 2. And from here, you will get your A exactly equals to 2. I mean, that's the proper way. Of course, from just now 4 to 2, we already can see it is second order. But those who can't see it, then you continue with this step and then go down to log both sides and then calculate A equals to a number. Then it show you 2 means it is second order. Now sometimes in exam, they may not give you an exact nice number like 2. Sometimes they give 1.99, 1.98. That's good enough. 0.99 first order. Alright, 0.0 something, 0 order. Alright, maybe not a nice number, but it's close enough to 0, first and second. Of course, we don't expect to get 3. Okay, so that's the second method to calculate the order of reactions. Is everybody clear? Alright, so this is how it looks like. I hope it's clear, but you can ask me again in tutorial sessions. So now we know how to determine the order of reaction. Next, we're going to look at how can we determine the rate constant. Alright, let's look at the example given here. So the oxidations of nitrogen monoxide occurs readily according to the following equations. Look at that. We have 2 reactants here, NO and oxygen. Ignore the products. And look at the table. Yes, we have the 2 reactants here with the series of different concentration and initial rate. Obviously, this is experiment 1, this is experiment 2, this is experiment 3. Okay, so they repeat the experiment using different concentration. Make sense? So the following data show how the initial rate change. It depends on the concentration of 2 reactants. Let's look at the questions. Use the data to determine the order reactions with respect to each of the reagent. Order with respect to NO. So let's look at that. NO. If we are looking for NO, oxygen must be constant. So which 2 experiments we should compare? These 2. Right? Constant, ignore. And 0.005 change to 0.01, which is double. Multiply by 2. And let's see what's the rate. The rate is 0.03 to 0.12 times 4. So what is the order of reaction? Second order. So is second order. Order with respect to NO is second order. And then what about oxygens? Let's check it out. Let me erase that. For oxygen now, so these 2, because NO is constant here. So 0.005 to 0.0075. So what's that? 1.5. Right? And then from here to here, 0.002 to 0.03. Again, 1.5. So what does it mean when they have the same change? They are proportional to each other, right? So that would means first order. As simple as that. All right. Next, write the rate equation for the reactions, okay, and use it to calculate the value for the rate constant and stating its unit. That's what we want to learn now. So we know the order of reactions now. So what is the rate equations? Rate equals to K concentration of NO, which is this second order, and then concentration of O2, which is first order. That's it. That's the rate equations. And how do we calculate the value of K? Making use of the table. All right. So I'm going to show you here. Since I have the value, it's easier for us to see the values. So again, I rewrite the rate equations, or the rate law equals to K concentration of NO square concentration of O2. Okay. And then I'm going to put in the values to calculate K. Let me change the color. Either experiments will do, guys. So let's say I choose the first experiment. So rate is 0.02 equals to K. Concentration of NO is 0.005 square and 0.005 power 1. All right. From here, I guess we can get the answer. Let's check it out. 0.005 square multiplied with 0.005, which is 0.005 cube, 1.25. So 0.02 over 1.25 times 10 to the power of -7, so small. All right, so 0.02 divided by the answer, you get this. K usually a big number, so 160,000, that's equals to your K. Okay, so that's your K value. And what's the unit? That's the main thing. That's the main thing. So how do we know the unit? Value's done. So let's check the unit. Now the rate equation is rate equals to K concentration of NO square oxygen power 1, right? So what's the unit for rate? It's given here. Mole per dm cube per second. So what's the unit here for the concentration before we look at K? So concentration term is mole per dm cube, obviously, and then you have power 2, power 1, so altogether power 3, cube it, right? And then to get K, of course, we use mole per dm cube over mole per dm cube. Sorry, this is mole per dm cube per second. Yeah, right? Because we move this over here to get your K. So then we divide them. So mole per dm cube gone. So this one, you still have one of it. So you still have 2 here. And then per second. So overall unit is actually mole -2, because you bring this up, right? And then dm6, no more negative. You bring it up, inverse it, and per second still the same. So that will be the unit for 160,000 for the rate constant. Now don't be surprised if you get a big numbers like that. Usually it is when the reaction is actually a feasible reaction. When we learned that in a previous topic. Feasible spontaneous reactions, the K value is usually a big value. Okay, the bigger the rate constant, the higher the rate of reactions. I mean, the more feasible it is. Okay, so that's the unit. We divide them. So different reactions, different order of reactions is actually giving us different unit for the K, for the rate constant. So for every single specific reactions, we have to calculate the rate constant and as well as the unit. All right, so it's different. So that's how we solve this question. Done. The answer here is 160,000 mole -2 dm6 per second. So that's the unit and the value. And use your rate equations in 2 to calculate the rate of reactions when the concentration of NO and oxygen equals to 0.0025. Now we have everything in the equations now, so we can just sub it in. So rate equation, again, I rewrite it. Rate equals to K concentration of NO power 2, NO2 here, and then O2 power 1, right? And then put in the value. Rate equals to unknown, because we are calculating rate for question 3. Rate constant 160,000. And then NO square. NO is 0.0025 square, which is this given. Oxygen is the same. Makes sense. It's supposed to be cube then. Power 1. So I split them. Then you just multiply them. You will get the rate of reactions. And from the unit cancelling out, you will get your rate as mole per dm cube per second. Right? So you get your value here. So this is for part 3. So once you got the all the reactions, it is very simple for you to calculate the rate constant, especially the unit, and then you can calculate whatever rate of reactions based on the concentration given. Yeah, that's the standard questions they will ask. Okay, guys. So that's it for this video. It's all about calculations for first, second, and zero order based on experimental data. So I'll see you again in the next video about reaction mechanism. Thank you.